David Smith here with another flipped classroom math lesson. A few tips before we start. First, remember that you can speed up or slow down the playback if that helps you follow along. Second, you can turn the captions on and read my words on the screen. Third, you can pause the video at any time to catch up with your notes or write down questions for class. Today's lesson covers transformations of 3 different types, and then each type has 2 types within it. This is going to be a little bit familiar to the transformations we did with quadratic functions in our last lesson, but I think it gets a little bit more complicated and there's a lot to keep track of. So probably the first pass through this video, you should just keep up with your notes, make sure you understand. Okay, so I prepared this table for you here to help organize the types of transformations. You can pause the video now and get this into your notes, or you can do it as I explain it, whatever works best for you. All right, let's get started. So the first type of transformation is a reflection. And what we're doing is we're changing this basic equation, y equals f of x. Remember, f of x is really just the result of putting in a number for x in a function. It spits out f of x or y. So what we're talking about is what happens to y when we make a change to the function. So first one is reflections. So we can typically reflect across either axis, the x-axis, which would flop us up and down, or the y-axis, which flops us left to right. So those are the types of reflections that we do. And so we have 2 kinds here, the x and y-axis. The notation that we're going to use here is that for the reflection across the x-axis, y equals negative f of x. So we're just changing the y value from positive to negative. And that kind of makes sense because instead of a point being up above the x-axis, now it's down below. So we've reflected it across the x-axis. This one is slightly different. To reflect across the y-axis, which is back and forward, we change the sign inside the function, and that generates a new y value based on that. Again, we're going to do some examples in just a minute, so hopefully this will come a little bit more clear for you. Dilations. These are expansions and contractions. When you dilate, you change the size. So we have 2 kinds of dilations here. We can dilate in a vertical direction, which also includes down, up and down, or horizontal, which is back and forth. The way a dilation works is you get a multiplier. So before you get your new y on your transformed function, you multiply it by some constant a. So remember, f of x is our y, but now we're multiplying it by a before we really settle on our y. And this is going to transform the y value by the absolute value of a. It's just going to make it that much bigger or that much smaller, depending on what a is. So you might think for a minute about what values of a would make it bigger and what would make it smaller. Now, a horizontal dilation is the same thing, except now we're going to multiply the x inside the function instead of after we run x through the function. So, and again, this changes the x value by the absolute value of a. One last type, translations. Remember, these are slides. We're going to move it back and forth or up and down. And the way we do a slide is we just add some constant to the result of our function before we get y. So we can add k, and that'll move the function up and down, depending on whether we add k or subtract k, and it's totally straightforward. If you have some function plus 5, it's just going to move the function up 5. Now, a horizontal is the one that's a little bit tricky, and if you'll remember from our quadratic section, that it's also tricky there. So again, we just add a constant, but instead of adding it after we do the function, we add it inside the function to the x value before we calculate. And so this would be x minus h. Now this is going to move the function horizontally, but in the opposite direction of whatever you see there. So if it's minus h, it's going to move it in the positive h direction. So that's why I put by negative h. You basically change the sign of what you see there in your function before you consider what transformation you're going to get. Okay, let's do our first transformation. Now I've graphed this function here. This is obviously a piecewise function. We have some rule governing this section, another rule governing this section, and finally a last rule governing this section. And these are all linear. We could figure out those rules. But for this activity or this problem, we don't even need to do that. So this function is y equals f of x. And we could denote that in piecewise notation and get all complex with that, but we don't need to. Because what I'm going to ask you to do now is graph y equals 2 times f of x. Before we do that, look at your notes or our table over there and tell me what kind of transformation this will be. If you said vertical dilation, you're correct. If you see here, we have the constant a times the function, times the result of putting in an x value. We just multiply it by some a. And indeed, that's what we're going to do here. We're just going to multiply the output by 2 to get our new points. So now I want you to pause the video and put this graph, transform with a vertical dilation and create the new graph right there. Let's see how you did. So what I did is I took my output of my function, my y value, and I just multiplied it by 2. Did not change the x values. This is only a vertical dilation, so it's only going to change in the y direction. So all the y values got multiplied by 2. So 6, 0 doesn't change. 0 times 2 is still 0. But my 2 on my 4, 2 became 4. So I'm dilating it vertically by a factor of 2. It's another way to say that. So the point 4, 2 became 4, 4. The point 0, 2 became 0, 4. And the point negative 2, negative 3 became negative 2, 6. That's positive 3. I hope you caught that before. So check it out. That is a vertical dilation with a scale factor of 2. Okay, let's give you another one. You might want to recopy this graph further down in your notes because you're going to transform this function by this rule, or you could just start a new graph and leave this up at the top, however you think would document the results best for you. So, check this out. Now I'm wanting you to transform y equals f of x using this function, y equals f of negative x. So pause the video for a second, look at your table, and tell me what transformation you're going to do. This is going to be a reflection across the y-axis, because that's this transformation here, y equals f of negative x. So what we're going to do is we're going to reflect this function across the y-axis. So now, pause the video and create that graph. Okay, let's see how you did. So you can look at the picture here and you can just see that this graph got reflected across the y-axis. But let's take a look at the points that are doing the reflecting. 2, 3 becomes negative 2, 3. That's this point. So we just change the x value when we reflect across the y-axis. The point 0, 2 is right on the y-axis. It doesn't go anywhere. Then the point 4, 2 becomes negative 4, 2. We're just reflecting 4, 2 over there, so that's reflecting across. And then finally, the point 6, 0 becomes negative 6, 0. So that's a reflection across the y-axis. So now we're going to do another one, and this one is going to be y equals f of 2x. So first off, pause the video, consult the table, and come back and tell me what kind of transformation we've got. So what we have here is a horizontal dilation from this section over here. Now, check this out. Remember, we did y equals 2f of x, and that was a factor of 2 in the horizontal direction. So now when we do a horizontal translation, it's different. Okay, so your scale factor is going to be 1 over 2. And we can go into explaining why, but technically the best thing to do is just remember that when you're doing a horizontal dilation, it's actually the reciprocal of the number in front of x. Think about the parabola. Remember when we had our a term, the bigger that number was, the parabola got compressed. When that number was a fraction, the parabola opened up wider. So this is going to compress our graph or multiply by a factor of 1/2. So go ahead, pause the video, and see if you can figure out what this function is going to look like under this transformation. Okay, let's see how you did. Now to do this compression, I just multiplied all of my x values by 1/2, leaving the y values unchanged. So 6, 0 becomes 3, 0, 4, 2 becomes 2, 2, 0, 2 doesn't change because I can multiply 0 by 1/2. It still stays 0, so that point does not move. And then negative 2, 3 becomes negative 1, 3. And this makes sense. My graph has been compressed. It hasn't changed in the vertical sense. It's still the same attributes that way, but it's been compressed by a scale factor of 1/2. Okay, complicated diagram. If you're in our class, this is in the book on page 140. So if you want, you can just make a reference in your note to look at the page 140 in the book. If you want to get it into your notes, that's fine. Extra practice always helps. If you're not in my class, you might want to jot this down. But the most important thing is that you be able to answer the questions to be able to see how to do this. So this problem is, look at the graph, generate the transformed function. So again, we have a bunch of piecewise functions. I don't have any function rules written out for these. We could do it. They're all straight lines. They're all linear. But that would be a lot of record keeping, a lot of messy just notation. So I'm going to skip all of that. So we're going to compare these three graphs, this red one, and this blue one, to our primary graph, which is the black one right in the middle. So this is function f. Okay? So we're going to compare the three others to function f, and we're going to say what kind of transformation they are, and we're going to write that general equation describing that transformation. Okay, so first task, compare to this one, and notice how I've given you some points, not every single one, but you should be able to figure it out. So you know some points of our function f. I want you to compare that to function g. That's this red one that's kind of spread out like that, and you can see some of the important points for g as well. So I want you to do two things. First one, say what kind of transformation that is, and then B, write the function for that. If this one is f of x equals y, what would you write for g? First question, type of transformation. This is a horizontal dilation. We've taken our w and we've just stretched it out. We have not changed it in a vertical way. We've only stretched it out. So we know we're going to have this form of our function. Now the only question is, what kind of a scale factor do we write in there? And again, let's take a look. Remember our last example where we had a scale factor of 1/2 because it was stretched out by multiplying x by 2? So pause the video and figure out exactly what to write as your function. Okay, if you look at the points, you notice that this point went from -1 on the x to -4 on the x. So we multiplied this by 4. So that means our scale factor is going to be 1/4. So our function here is going to be f of 1/4 x. That is going to be the notation for this transformation of our w function, for our horizontal dilation. All right, let's do this function. So now I want you to pause the video and first off, figure out what kind of transformation gets you from our first black W to this one. It's upside down and it became an M and it moved around a little bit. So pause the video and see if you can figure out what kind of transformation or transformations got you from here to there. Okay, the type of transformation. Our W, our M, they're the same size. So that tells us we have not had any dilations. Okay, so we can strike that one off the list. However, we have had two types of transformation. We've reflected it across a horizontal line, and we have also slid it over and up. So this one's going to have a fair amount of stuff to it. It's not going to be quite as simple as this function. Go ahead, pause the video, use what you know about the table, and write the equation for r of x. Okay, let's handle this in a step-by-step way, okay? So first off, I know I need to do a horizontal or a reflection across a horizontal line. In this case, it's not the x-axis, but actually it would be the x-axis. So I would just put my minus there, and I'm going to take this and I'm going to reflect it in place across the x-axis. So that's the minus, and then the rest of this is about moving that reflected figure over and up, okay? So when I reflect, just remember, I'm not going to reflect it from here to here. I'm reflecting it across the x-axis. So that goes right in place like that. So that's my minus. Now that I've reflected it and my W is now an M going the other way. Now I need to move it over. And I'll notice that this one, this point in the middle is at -4. This one's at 0. So I've got to go 4 that way. It's negative direction. But remember, when we go to the left, inside, it's actually a positive number. So that gives me x plus 4. Now that I flipped it, I'm still down here. And I need to go up a whole 5 to get all the way up to where this is. So that's the +5. So to get from this W to that W, what I need to do to my equation is I need to do negative f of x plus 4 plus 5. Okay, last one. Now we got this big stretched blue W. So I want you to pause the video and first just come up with the transformations that get you from here to here. What are they? All right, we have 3 steps. I'm going to do the vertical dilation first. Notice how this has been stretched up quite a bit, but it's still the same width. We haven't stretched it out in a horizontal way, so we've done a vertical dilation, and then we've also moved it to the right and up. So we have a horizontal and a vertical translation, or a slide. So we have 3 different transformations of this function. So now I want you to pause the video and write the function for this transformed graph. All right, let's take a look at this because it's a little bit tricky. First off, let's take a look at the vertical dilation. We have taken this graph from going from the range in y values is 4. So we're doubling that because this one goes from 0 to 8. So our vertical translation is just by a factor of 2. We're just multiplying that by 2. So I put my 2 outside. That's just going to take whatever happens inside and double it. So basically what we did is we just doubled our height of our function. So that's good. Now we can also see that we had to move this over 5 to get it to line up horizontally. So we moved it 5 in the positive, but inside the parentheses that shows up as a negative. Now the last one is it's a +4. We had to move it up by 4. Now think about that for a minute, because it seems to me like really you only moved it up 2, right? Our bottom points of our W are here, and now the bottom points are there. But there's something going on that means that it actually has to move up by 4. See if you can figure that out. Okay, here is what it is. When we stretch this by a factor of 2, it's true that the distance between the top and the bottom is 4, but we're not going to stretch it up only. We're going to stretch it up by 2 and down by 2. It stretches in all the directions. So the stretch is going to make it go like this. So the tops only move up by 2. So this is going to be over there, and it's going to be stretched out. I didn't make mine quite right, but it's going to be stretched out to this size. But these are going to be 4 down from these. So you're going to have to move the whole thing up 4, not 2. So remember, dilations happen in both directions. If it's a vertical dilation, it's going to go up and down by the same amount. There's actually an important point here that I realized while I was editing the video, and I did not cover it. So I'm just going to jump right in here and give you that point. The thing to realize with this dilation that we just talked about is that the dilation occurs vertically, and it occurs around the x-axis. So if you have a figure that straddles the axis, the points below go down and the points above go up, which is what makes this complicated. If the W was wholly above the x-axis, then it would only move upwards. But instead, it's going to stretch down and up because it's going across the x-axis. And that's because we take these numbers, these coordinate points, and we multiply them. So if you're at a -2 and you multiply it by 2, it's going to go -4. Whereas this 2 went +4. So that's how come this dilation stretches across the x-axis. And the same thing for this reflection that we did here. Initially, I thought that maybe it would reflect like that, like reflect across this horizontal line. But actually, it reflects across the y-axis. So it reflects in place, like I said. If it was all the way up here, then it would reflect completely across the x-axis. So things get complicated when a figure or a line or a graph crosses an axis and you're doing a reflection or a dilation. Now that you've finished the video, take a moment and jot down some notes or questions for our next class. Remember that you can also watch the video again if you want to increase your understanding. If you enjoyed the video, please click like, and if you'd like to help me grow my YouTube channel, please click subscribe.